Hello and welcome to Chemistry of the Air. That's all. We're joining the class in progress. We just took up, and I'll just flash to the screen, we just took up our conjugate acid and base questions from yesterday. I'll just, if you need to pause the screen to see them, there they are. There these are. We talked through them. And slowly, we are. And right now, we're jotting down some notes. We're going to work through this example as a group. Good. Okay. Okay. Most acids we use are mono, one proton, monoproton, one H plus. Some have 2 or 3 protons, 8 pluses for donation. We're going to learn, though, that they don't donate all 2 or 3 at the same time. It's still one at a time. I've instructed you so far, if you see something like H2SO4, just take one H off and we'll continue. Phosphoric acid is a tri-3 proton, triprotic acid. Write the dissociation equation for each proton. And phosphoric comes from phosphate, H3PO4 is what it'll turn out to be. That's the ion. So first thing is losing the first proton. We're going to write out an equation. We'll do this as a group. Reason students. But you know in the future when I have questions like that. Of course, I can space my pen. So I'm going to start with H3PO4. Good. And we know how I came up with that one. H plus, H plus, H plus with the 3 negatives. We're going to add it to water. Colors. I'm telling you it's phosphoric acid, so it's going to act as an acid. It'll donate one of the H's. We're losing the first proton. H2PO4. Now I've taken off an H plus, so we had H2PO4 has 0 charge. So this one will have plus plus, negative 1. And we add it to water, called hydronium. Okay. We've got that. It would only happen one at a time. But if I make conditions right, like this, you can lose the second proton. H2PO4 negative. Now remember, this would be in, say, I'm telling you, this is in a beaker of water, let's say. So there's plenty of waters. H2O. Now, when this loses the second proton, we're down to 1H. HPO4, but this time 2. Once again, hydronium ion is formed. You see that big acid, H3O. Everything acids added to water form H3O. And to lose the third reaction, the third proton, start with the HPO4. In water still. Now it's down to PO4 3 months. No more to lose. Now nothing will live. Okay. So it happens actually in 3 stages. Never happens at once. But I'm going to show you the net reaction. You know Hess's law? We added reactions last year. Maybe you did, maybe you didn't. Energies, that's delta H. Okay. Well, the net reaction, I'll explain it. Start with this, right? Becomes this. But then this is used up over here. It's sort of like math. You got an x on the left side of the equation and an x on the right side of the equation. You can cancel, right? Same with this. This is why I color coded this. It's easy to see. Those cancel out, right? None of the waters cancel out. None of the H0, the hydronium ions cancel out. You'll notice red and green cancel out. So my net reaction really is H3PO4 is what you start with. There's 3 waters. They never just the end result is that you get PO4 3 minus. 3 groups of hydronium. Okay. That never happens in one step. But just showing advanced reaction. Not all that useful, but probably. So I'm going to tell you about what we're going to do in the class right away. Strength versus concentration. And I want, this is vocabulary and understanding how they are different things. The degree of acidity, it's a lab activity. And what we're studying really, do acids have the same, of the same concentration, have the same level of acidity? We're going to call that pH. You've heard of pH. It describes something which we will understand a little more further in the week. We're going to have a special pH paper that doesn't just tell us litmus paper like acid or base. It's going to tell us the pH 1, 2, 3, or 4 and stuff. And we have every solution is decimal 1. What I do want you to copy out is this chart. That's it. We're going to use pH paper, and you guys know colors. I don't. And you're going to tell me about this. Okay. I'll pause the video. We'll do the activity, so the video won't have much to show for the next while. After doing this, we see something. They all have the same concentration. That's the moles per liter. So the concentration of an acid won't tell you necessarily how dangerous it is. Vinegar, like it's actually acetic acid is the stuff. It doesn't have as acidic a pH. It has a higher pH, which doesn't mean it's stronger, right? It's actually weaker. As far as the, well, I won't get into what pH describes yet. I'll leave something for tomorrow. Okay. So then, I want you to not take notes on this, but strong acids, weak acids. Let's read through this as a group. Okay? Strong and weak acids, because we can't tell by just their concentration. It has something to do with it. Strong acids are completely dissociated, 100%. Dissociated or ionized, actually, is a better word. They go one way. They aren't equilibrium. If the acid is less than 100% dissociated, we say it's weak. Doesn't mean it's not dangerous. The Ka of the strong acids are very high, greater than 20. And 20 is, bigger than 1 means it favors the product side on a K value, right? Equilibrium. We're going to talk about the table of acids. Okay. Now, I want you to get your periodic table handout set up because we're going to take a look at this. So I'll pause the video while that's happening. On your periodic handout set, at the top of the page it has a list of acids, pH values. It's in the middle of it. Find them. Okay. You have your periodic table handout set. You found this. Your Ka values are on the right-hand side, but it's not that much. The top 6, I want you to put up bracket around it or something to label that they're strong. Okay? Those are all greater than 20. 24, 2.4 times 10. So you're going to label your periodic table strong, tough. Anything below that is considered weak because the Ka values are small. But they're in numerical order. Okay, a few things then about those 6. I won't require you to memorize which 6 are strong acids. I'll actually say in the indicator. But the chloric acid, I've actually never used that in a high school or even in university. I don't know, like paper problems, but I mean, I've never had it. I don't see any reason to order something nasty like that. Hydroiodic, hydrobromic acid, hydrochloric acid. Where are those 3? How are they connected on the periodic table? HI, HBr, HCl. Yeah. They are all diatomic, and they're in the same 17th column, the halides, halogens, stuff like this too. They're in the same family, so they form similar acids. And you notice it gets weaker as you, like I is the lower one on the periodic. As you climb up, it's still strong. But then HF doesn't appear. Okay. HF is not considered strong acid because it has a 10 to the minus 4, 6 times 10 to the minus 4 Ka value. But it's still very dangerous, actually. And I think I mentioned this one. It eats through glass. It's used on Breaking Bad to dissolve a body, I think. I think it was that. Anyways, it is nasty. You do not want to come in contact with that. Okay. Then sulfuric and nitric acid. You already know, I think, 3 of these strong acids anyway. So in university, I had to have these memorized, but that's universal. But to tell you the truth, I think you know of nitric acid, sulfuric acid, and hydrochloric acid. A lot of grade 8 and 9 students would know of those names because they're strong acids, and you hear about them in the news sometime or in movies. So those ones are strong. Everything else will be considered weak. And it's only because of their Ka values. They're still dangerous. Why? Okay, so weak acids just mean it has a low K value. Well, that means then that it's equilibrium. The other Ka values are so high that we just write a one-way arrow. That's all I need you to get out of that, but I need you to have it. Now, as far as, and I'm going to just, that was silly. Oh, well, whatever. I did it the other way around. I'll just clear the ink off here. Try this again. Someone's memorized it already. I thought it was clear. I used to have the answers underneath. Okay, anyways. So concentrated and dilute are relative terms. There's no magic number, but generally, let's say something that's concentrated, usually it's bigger than 6. What if it's 6? Well, it depends. You know. Dilute acids are generally smaller than 6. Okay? So, can you write this down? The concentrated acid, if I say it's a very concentrated acid, greater than 6, dilute, less than 6. And I'm not going to trick you to put down 6. Okay? Concentrated. That's strictly the moles per liter. Nothing to do whether it's a strong or a weak acid. So this is why I have these 4 here, and every combination possible. I want you to complete this chart using your ion chart, and the 6 moles per liter or higher or lower. HF, I actually already mentioned it. It's strong or weak, concentrated or dilute, etc. I'll give you guys some moments to do that, and we'll take it up. Okay, we'll do one category. Oh, one category at a time. So, I'm going to do concentrated or dilute first. That's strictly done by the concentration, moles per liter. 12 moles per liter HF. 12. Bigger than 6, so I'm going to say it's concentrated. Oh, there was our magic. 0.02, definitely less than 6. Dilute. Still is dangerous. 12 molar HClO4. And 0.3. Okay, dilute. Now we're going to have every possible combination. Strong or weak? You have to use your chart. See, HF, is it one of the top 6, or is it a Ka value less than 1? Less than 20, but they're all less than 1 on that chart. The ones that we have. Anyway, that's not every acid in the world. If you ever come across something that isn't on there, you could Google it up nowadays. I used to have this fat book. This book here. I used to look up stuff before Google. It has a lot of things, not everything new. Okay, anyway, HF. Is this strong or a weak acid? As I mentioned before, it is weak. It's Ka value less. HBr. Strong is one of the 6. HCl is strong. 4. So find that. That's not hydrochloric acid. What is that? Yeah, what is it called? Well, yours doesn't have the names on it? Ah, okay. I forgot. Perchloric acid. That's definitely strong. It's the strongest one. It's the top one, right? Perchloric acid, isn't it the top one? Yeah. Okay. Now, HClO. Perchloric acid is HClO4. We're looking for HClO. My chart's organized a little different. So weak, hypochlorous acid, 10 to the minus 8. Definitely weak acid. So what I want to get across to you, though, is that you're going to have a weak but concentrated acid. You're going to have a strong but dilute acid. Doesn't make it safe. You're going to have a strong and concentrated acid. Stay away. I'd be wearing gloves. I wouldn't have this stuff. And weak dilute acids. Every combination is possible. They're all of suspect safety, though. Treat every acid as if it's dangerous, and I'm serious. Like, okay, you're handling vinegar. I think you understand that you don't need gloves because you use it in the kitchen, right? Okay. Use common sense.